Hello, we're looking at definite integrals today. In the recent video sessions we've looked at indefinite integrals when we've had the integration of the constant or constant integration, and that gave us an idea of how we take an antiderivative from a derivative and then vice versa. What we're looking at today is we're looking at getting an exact answer. So what we looked at in this video before this lesson is we looked at something called upper and lower rectangles, or what we call Riemann sums. And that kind of gave us an idea on how we find an area, an estimate of area underneath a curve. A more accurate way of finding those areas is called using definite integrals. Now we're not going to go into the video and say using that in terms of finding an area, but we're going to look at the understanding of how we use definite integrals to find that area more accurately. So for instance, if we did have a graph, just as this graph here, and this here was our area between, let's say, 0 and 4. We can use definite integrals between these two bounds. So beforehand, we had no way of doing this just using Riemann sums. So we had to use right angle triangle or right and or left hand rectangles to help us estimate this area. But what we can do with indefinite integrals is we can actually use the equation of this, integrate it, and then substitute the values for x and 0 in there to give us a understanding of the area between these 2 points underneath that curve. What we're going to be doing today is we're not going to be looking at finding the area underneath the curve, but we're going to be calculating indefinite integrals. So in order to calculate those indefinite integrals, we've got to start off with an integral. And we know that if we had an integral between b and a, and we had a function of that, what we had before is we did not have b or a in this purpose. These here are what we would call your upper bounds and your lower bounds. So on this sketch that I just erased, 0 to 4, 0 would be your lower bound, so that's where a would go. And 4 would be your upper bound, so that's where b would go. And then we would use the function here when we integrate it to get the entire area. So if we look at this up here, if we were going to integrate this, this would become the integral, or when we integrate it, our antiderivative of b on a. And how we calculate this is by taking the integral of b and substitute that with the integral of a. And this here is the answer that will give us that exact kind of area that we're trying to calculate. When we're looking at indefinite integrals, we're trying to get an accurate answer, and these use more, has a better understanding when we start applying it. But if we don't know how to actually calculate that, there's no use applying it. So this up here, I'm going to leave this up here for a second, so when we do the next examples, you can see the process that I'm taking follows this process. This is not the rules as such, but a process of how we actually integrate. So we do have some of those rules, and some of those rules that we already know have been learned in indefinite integrals. So such as remember we had, if we had an integral of say some function of k f of x dx, and we have b a here, we could rewrite this here as k, the integral of b a fx dx. So we can apply this same rule we use with indefinite integrals, we can apply to definite integrals, because we're not actually integrating the constant, we're integrating the function. So when we start looking at this, we're going to have a look at an example where we can integrate this in terms of the function instead of the constant. So let's get into an example. And I've got some examples on the board over here. So let's do the first one. We've got 4, 1, 6x squared minus 5 dx. So this is our first step here. Our next step is we need to integrate that and then apply our boundaries. So this here would become 6x to the power of 3 all over 3 minus 5x, which we could simplify down to 2x to the power of 3 minus 5x. I'll make those brackets bigger. And all to the boundaries of 4 and 1. So what we've done here is we've integrated to get to this point. That's this point we're looking at. And now we're going to take, let's substitute the value of b, in this case 4 for all the x's, and then subtract from that all the values of a substituted for all the x's. So we have two brackets, 4 cubed minus 5 to the power times 5 times 4 minus 2, 1 cubed minus 5, 1. If we work all this out, we're going to get 128 minus 20 gives me 108 minus what we got 2 minus this will give me minus 3. So we've got 108 minus 3, which is the same as adding, so therefore we get 111. Well, we won't say units, our answer is just 111 because we're not dealing with area. So when we're looking at this in terms of definite integrals, we're following this process. We integrate and then we substitute the boundaries in to get our answer. Alright, let's have a look at the second example. So, second example here, we've got 4 to 1, but this time we've got a square root of x dx. We need to get rid of that square root first, so let's change that into a power. So we'll write this up here, is equal to the integral of 4 to 1, x to the power of a half dx. And now I can start integrating this value out. Let's integrate. We get x to the power of 3 over 2 over 3 over 2, which we can rewrite as 2/3 x to the power of 3 over 2, which can give us 4 to 1. Now, we can do this a different way. This here could kind of look quite messy because we've got fractions and fractions going on everywhere. What we can do here is we could rewrite this here as 2 over 3 x square root x. And you're going to get that same answer no matter what. Only difference between here is that we're dealing with fractions, which sometimes can be a little bit difficult, whereas we're dealing with these square roots in its place. Okay, so let's look at it. So we would then have, this is equal to 2 over 3 brackets, 4 to the power of 3 over 2, minus 2 over 3 brackets, 1 to the power of 3 over 2. Alrighty, so let's get the answer and plug into the calculator and see what we get. So we get